Great. Thank you, and thank you for coming back. Let me just start by recalling what I did yesterday. So just a quick recap. So the idea was, so given X a smooth surface and F a one-dimensional foliation with reduced singularities, the idea was that we wanted to simplify the geometry of F by contracting curves. So the idea is that what we would do is we would find a sequence of birational contractions. So we are contracting curves, which are generically leaves, so invariant by F, such that one of two things happens. So let's say, so we have F, and then we have a natural way to transform F to a foliation F prime on X prime, so such that either we're in the case where our foliation F prime comes from a P1 bundle structure. So we have a P1 bundle, and F prime is the foliation induced by this P1 bundle. So the leaves of F prime are just the fibers of the P1 bundle. And then the other possibility is or we end up in a case where KF prime is Nef. So maybe just to make another quick remark about this. So if you recall, I proposed one one attempt at classification based on the uniformization, or what the universal cover of the leaves are. So so my remark is that if Lx is a general leaf and Lx tilde is the universal cover, then if Lx tilde is P1, so if the universal cover of the general leaf is P1, we always end in case 1. So again, if the universal cover of the general leaf is P1, we're always going to end up in case 1, namely the foliation comes from a P1 bundle structure. And otherwise, so Lx tilde is C, or the disk, we always end in case 2, i.e. Kf prime is Nef. So you can, I guess I just mean to say that there's no mystery about how the MMP, how this program will terminate. You know right off the bat, as soon as you look at your foliation, which one you have to end in. Yes?
What do you mean by the universal cover being P1?
So if you're, I guess, general leaf, you pick a point, your general leaf, if the leaf through it is isomorphic to P1C. So by the, this is a one-dimensional Riemann surface. A Riemann surface, and it has a universal cover, which is either the disk, the C, or P1. And so if it's P1, then, well, we have to end in a P1 bundle. Yeah, is P1, yeah. So. Yeah, exactly. Yeah, Lx is P1. Yeah. Okay. Okay. So now there was a slight subtlety in this whole story, is that usually X prime is singular. So we had an example where we actually showed that quotient singularities can arise in the course of contracting these curves. And so as a result, we saw that reduced singularities, or the class of reduced singularities, was not the right class of singularities for running this program. And so we introduced a new class of singularities called canonical singularities. And so just to recall what the definition of canonical singularities was, so we said that, so X is a normal variety. This is not so, this works in all dimensions. So if X is a normal surface, F was a foliation. Then what we did was we measured the singularities by these things called discrepancies. So if we have, let's say, P from X tilde to X is a sequence of blowups, any sequence of blowups. So we have to consider what we could do is we could write KF tilde, the transform, so the pullback of KF, as P star KF plus some numbers A, EI, F, EI, where the EIs were our P exceptional divisors. And then we said that F was canonical if A, EI, F was bigger than or equal to 0 for all EI. And again, we have to run over all possible sequences of blowups. And then I also defined what I meant by log canonical singularities, but maybe I'll skip over that right now. So one of the key points about canonical singularities is that, so I didn't get a chance to say this yesterday, but canonical singularities are preserved by minimal model by the minimal model program. So these steps of this program I proposed. And so the proof of this fact is pretty easy. So let's say we have a single step in our program. So C contracts, so call this F, we'll call the push forward to Y, Fy. So C contracts a single curve E such that Kf dotted with E is negative. Okay. Now, if we have some sequence of blowups over Y, well, by perhaps passing to a higher model, or doing more blowups, we can assume that we have a birational map down to X. So we have P, or something calling it C, and then we have Px and Py. And the thing to observe is that, so by assumption, and we have, I guess, a foliation Fw, F, Fy. So by assumption, we're assuming that F has canonical singularities. So we have that K of Fw is just Px star K of F plus Ex, where Ex is some Px exceptional divisor, which is effective. Now, because Kf dotted with C is negative, this tells us that K of Fx is the pullback of K of Fy plus Ae. Now, E squared is negative, so A has to be positive. So again, we see E is a contractible curve, so we know that E squared has to be negative. So note E squared is negative. Yes, dot E, thank you. Yes, perfect. And then then we put this together, and this tells us that K, so we just put these two facts together. These two things imply that K of Fw is Py star of K of Fy plus Ex plus Py star A E. But this whole thing is again effective, which is our definition of Fy having canonical singularities. So again, I just want to emphasize that it's for just sort of, the MMP is, or canonical singularities are set up in such a way that they're automatically preserved by these operations. So whenever you're contracting things which are negative with respect to Kf, canonical singularities are always preserved. Okay, so this was a quick summary of what happened yesterday. I want to turn my attention now to thinking about how this story works in higher dimensions. But before I do that, I guess I want to ask if there's any. Want to check if there's any questions about the surface theory before I go on. Yes. W. So to check if something's canonical, we have to think about. We have to compute the discrepancies on all possible birational models. So W is just some sequence of blowups of Y, and then perhaps passing to a higher birational model, we can assume that it maps down to X. Yeah, thank you.
So canonical in minimal model means sort of singularity which has positive curvature or negative curvature in a sense.
In a sense, yeah.
Is there any, so do we have the same intuition here with respect to foliation and protocol?
Yeah.
That formula envelope and we don't pretend to any geometric intuition.
So yeah, so maybe I guess the problem, yeah, is that when it's a foliation by curves, it's maybe a bit obscured if there's any sort of comparison, because I guess, like, what does canonical singularities mean? When you have a single curve, canonical means it's smooth. So from that perspective, at least in low dimensions, maybe any sort of comparison is obscured. But I think as we move to higher dimensions, it's easier to see what this analog would be between the two. So maybe as we move through this, I'll be able to answer your question a bit more precisely. Cool. Any other questions? So I want to look at a concrete example of what's happening in dimension 3. So in dimension bigger than 3, new things occur. And I want to give a concrete example of this. So the idea, so let's look at a pretty simple case. So let's consider P1 cross S fibered over S. And so this induces a foliation, just the P1 bundle structure. And then I want to blow up at a single point. So this is a blow up at some point. And so if I look at what this thing looks like, so here's S, and then the general fiber, and so the general leaf of my foliation, so maybe I'll color that in red or orange, is just a P1. I have an exceptional divisor, which is a P2. I have the broken fiber, which will be a leaf of the foliation. And then on the exceptional divisor, the foliation looks like a pencil of lines passing through the point where it meets the broken curve. Okay. So my goal, again, my goal is to do KF negative contractions. So if we call this foliation F, what we can check is that K of F is exactly equal to the blow up or the pullback of the relative canonical bundle, so K of P1 cross S over S, plus E, where E is our exceptional P2. So this is a good exercise to check this. And so what this tells us is if we we have two special curves to look at. We have a special curve C, which is our broken fiber, and then we have a special curve L, which is a line in our P2. And what we can compute is that KF dotted with L is equal to -1, and KF dotted with C is equal to -1. Now, our goal was to contract KF negative curves. So we have a choice now. We can either contract L or we can contract C. And so what we'll see, and if we contract L to a point, well, contracting L, the only way to contract L is to contract E to a point. So we end up back where we started. So that's not so interesting. So choice 1 is to contract L by sending E to a point, so just undoing our blowup. That's completely valid, and we're just undoing the blowup. So that's one option. But the other option is, well, we can contract C to a point. So in fact, the normal bundle of C inside X is just O of -1 plus O of -1. So we can really contract it to a point. And so we have a map X to Y, which contracts C and only C to a point. This is what we call a small contraction. So it contracts a subset of codimension at least 2. But what I claim is that something problematic happens here, is that if G, so call our contraction P, so if G is the push forward of F, so the transform of F, so my claim is that KG is not Q Cartier. And I'll prove this for you now. Well, so proof, if KG were Q Cartier, so suppose for sake of contradiction that it were Q Cartier, it would have a well-defined pullback. So the pullback of KG would be well-defined. But KG, Y and X are the same away from a curve. And so if you have two divisors which are the same away from a codimension 2 subset, they're the same divisor. So actually, we have to have that the pullback of KG is just KF. This is because they agree away from a codimension at least 2 subset, again, namely our curve C. But this is our problem. If KF is the pullback of KG, then by push-pull, KF dotted with C is the pullback of KG dotted with C, which has to be equal to 0. But this is a contradiction because we assumed that KF dot C was -1. And so this is impossible. So again, this is the first example of a very general phenomenon which happens in dimension 3. This can't happen in dimension 2 just because there aren't enough dimensions for this to happen. So this is a new feature of dimension 3 geometry. Okay. The reason why this is such bad news is that if it's not Q-Cartier, we can't make sense of Neff-ness anymore. So nothing, our whole goal to make KF Neff is senseless now. So I guess, remark, without Q-Cartier, Neff-ness, or the notion of Neff-ness, does not make sense. So our whole program stalls out. So the whole rub, and I guess the whole spice of three-dimensional geometry comes from trying to repair this issue. And so I want to explain the way we repair it. So let me move this one. Oops. Okay, so yeah, just to emphasize, if we're contracting a single curve on a threefold, we run into problems. And so we have to do something else. Are there any questions at this point? And so let me explain how we fix this. So we fix it through something called a flip. And I'll explicitly construct the flip in this case. So I'll give a general definition of what I mean by flip later, but I think it's important that you see the first example of it, or one example of a flip before I just throw it at you. So where's my orange? There we go. So what we're going to do is we have our foliation. What I want to do is I want to blow up C. So maybe I'll write it later. So when I blow up C, well, okay, the normal bundle of C was O of minus 1, O of minus 1. So when we blow it up, the exceptional divisor is a P1 cross P1. So this is the blow up of P2 at a point. And then this is a P1 cross P1. And our foliation is going to look something like this. So the foliation on these two, these are both P1 bundles. It's just agreeing with the P1 bundle structure. And again, just to maybe emphasize the direction things are going, the fibers in this direction, we're contracting in this direction when we blow up C. But now we can blow, so we blew up C, and we got a P1 cross P1, but now we can blow down the P1 cross P1 in a different direction. So we contract the P1 cross P1, but going in this direction. So maybe what I'll do is I'll emphasize that this is my blue arrow, and this one is my green arrow, and now I'm going to contract in this direction. And now what I get is just P2 blown up at a point. Now this all still maps down to S at every step. I want to emphasize that the foliation, the map down to S is not the same the leaves of this foliation are not the fibers of the map down to S. I just want to emphasize this point. This factors through the blow up at a point of S. And that map really gives you the right fibers. So that's why we call it a flip. We had a curve that was hanging off of our P2, and we just flipped it into the P2. So maybe I want to emphasize that my flipped curve is in here. So I had C, and then I'll call it C plus over here. and this is a flip. And to emphasize, so again, this is a good exercise, is to check that so if we have our foliation, call it F plus over here, KF plus dotted with C plus is now actually equal to 1. So we had the problem that on this side, KF dotted with C was negative, but then we flipped it and we made it positive. And this is the general strategy to fixing these kinds of problems. Okay. Okay, so this is I think a nice concrete example. I want to emphasize, though, that in general, it's much harder to picture what a flip is. I don't think there's a general way to really see what these things are. I'll give a general definition, but it's a bit opaque geometrically what's going on. But I think this is a nice, very concrete way to see what's happening. Okay, great. Any questions at this point? So now I want to talk about how we run the MMP in higher dimensions. And the idea is it's going to come down to proving a bunch of theorems. So yes? Yes. So yeah, this is a KX flop. Yeah, it's the Atiyah flop actually. So yeah, if you heard the stuff, this is it's a KX flop. And yeah, let's call the Atiyah flop. Cool. Any other interesting comments? Okay. So the first, okay, so I promised, so I guess, well, George called me out, and I promised I would make amends for that. So the first thing I have to define for you guys is the Kleiman-Mori cone. So in higher dimensions, I guess philosophically, it's not the right thing to look around for curves to contract. Rather, we should be looking for what are called extremal rays. And so I have to define some stuff, namely this. So this is the closed convex cone in H2 XR. So if X is smooth, it's H2 XR. Otherwise, you work in Néron-Savary. But if X is smooth, just to be concrete about things. So it's the closed convex cone in H2 XR generated by the classes of curves C, so in H2 XR, where C is a curve inside X. So maybe just to emphasize, so if this is H2 XR, the Kleiman-Mori cone is just some cone inside this high-dimensional vector space. And the key thing we want to look for are what are called extremal rays. So So there's a lot to be said about the geometry of this cone, which I won't really have time to talk about, unfortunately. But so a ray is a one-dimensional subcone. So a ray inside this cone, so a ray, so again, one-dimensional subcone, is called extremal. if whenever, so this is just a definition from convex geometry. So whenever alpha and beta are just two elements in NE bar X, and alpha plus beta is an R, then, in fact, alpha and beta were in R to begin with. So this is, again, these are the objects we want to be working with. To make it more down to earth, I just want to remark that if X is a surface and C inside X is a curve such that C squared is negative, then the ray spanned by C is extremal. So I just want to emphasize that this, I guess, more abstract definition coming from convex geometry really does generalize the more down-to-earth notion of a curve in the surface with negative self-intersection. And again, the point is that the way the program works in higher dimensions is that what we're looking for are negative extremal rays. So I guess this is another sort of silly remark, is that if K of F is not Nef, then there exists a KF negative extremal ray. On which and so again, the shift in higher dimensions, the shift that occurs in higher dimensions is that we shift from trying to study KF negative curves to studying rather KF negative extremal rays. And this is the first sort of shift. And again, you can check that in our example upstairs, both C and L, they span extremal rays inside the Kleinman-Mori cone in this case. Okay, so I just threw a lot of notation, and I'm about to throw, what I'm going to do now is I'm going to write down a series of, I guess, conjectures to explain how this program is working. So I'll pause here before I throw up all these theorems to see if there are any questions. Yes?
What can you say about the cone near intersection with KF? Like, is it concrete for
Yes, so actually, yeah, you've anticipated my next theorem. So yes, perfect, yes. I will answer your question shortly. Okay, so anyone else want to take a guess at what the other theorems we're going to write are? But okay, that was pretty good. Thank you. Oops. There we go. Okay, so in higher dimensions, the minimal model program is a consequence of a bunch of theorems or conjectures. So in the running, I'm going to have a running hypothesis here. So I'm going to assume that X is KLT and Q factorial. I know I haven't defined KLT for you guys. I don't want to overburden things with notation. So you can think, so I guess I'll just say that as we know, so as I explained, in the course of doing things, our underlying variety becomes singular. This is a class of singularities which is preserved by the MMP. But you're not going to lose much of the general flavor of things if you just think either smooth or quotient singularities. So in terms of getting a big picture, you can just imagine, instead of me saying KLT Q factorial, you can just imagine I'm talking about a smooth variety or even a variety with quotient singularities. again, you're not going to lose much of the general flavor of things. And F is a foliation with canonical singularities. Okay, so maybe I'll call these a bunch of conjectures. So the first conjecture is the cone conjecture. So it says that if R is KF negative, so R, again, inside the Kleiman-Mori cone, is extremal and KF negative, then there exists a rational curve L, so, or maybe I'll say P1, there exists a rational curve P1, P1 to X, such that R is spanned by the class of P1, or of the image of this P1. So in particular, it's KF negative. We have that P1, I mean, the intersection of this curve, so maybe I'll write this as F of P1 dot, so negative F P1 dot with KF. It has bounded negativity, so it's at most 2 times the dimension of F. And also that F of P1 is tangent to F. So we have three features. The next conjecture is what we call the contraction conjecture, and which says that there exists a morphism, so R from previous, so there exists a morphism X to Y such that C of R of a curve sigma, so sigma inside X is a curve. This is a point if and only if sigma is inside our ray R. So yesterday I kind of alluded to a cone and contraction statement. This is what I meant. Now, if the exceptional locus of CR is codimension at least 2, so e.g., it's a curve in a threefold. So in particular, CR is not a fiber type contraction, so it's not a fibration, and CR is not contracting a divisor. So in every other case, the transformed foliation is not Q Cartier. And so to repair it, we have to do what we call a flip. So in this setup, a flip exists. So and I'll write down what I mean by a flip. So i.e., so a flip is just a diagram of the following form. Okay, this is good. So I'm gonna erase this picture of a flip, and I'll replace it with the full definition of a flip. So by a flip, I mean a diagram of the following form. So x, y, x plus. So here's our contraction CR. Here's a contraction CR plus. And such that the following holds. So phi is an isomorphism away from a set of codimension at least 2. So again, in the example I erased, so away from a bunch of curves, it's actually an isomorphism. And 2, kf plus. So we have a way of birationally transforming f along this birational map, is CR plus ample, i.e. kf plus dotted with sigma is positive for every curve, for all sigma, such that CR plus sigma is a point. So it's positive in the exceptional direction. And I guess, and the other thing I guess I want to emphasize is that the relative Picard rank, I guess this is redundant, but just to emphasize, so this is equal to rho of y plus 1. Okay, so this is the definition of a flip. I think perhaps it's kind of unilluminating geometrically what's going on. This is exactly what we have to do to fix. It's just by definition the thing which fixes this problem of you lose Q Cartesianus here, so the only way to fix it is just to create some other model over here on which the transform foliation becomes ample on exactly those curves where it was negative. So you're cutting out the curves where KF was negative, and you're just kind of jamming them back into into X in a new way, which makes them positive for the foliation. Again, I think maybe it's a bit opaque geometrically what's happening in this picture, so that's why I wanted to start with the other diagram to really just drive home the fact that there is a concrete geometrical picture to be had here. Okay. And then the final theorem, or conjecture, is that there's no infinite sequence of flips. So there's no of flips. So how do these four conjectures come together to prove our goal? So we get the minimal model program from this. Okay. So let me, I guess, bring up these two, and then I'll explain how this works. Okay, and so now we can run this algorithm. So the first question we ask ourselves is Kf Nef? Well, if yes, we stop. That's one of the things we wanted to do. We wanted to make Kf Nef. So if it was already Nef, we just stop. There's nothing to do. Otherwise, so if no, then there exists a Kf negative extremal ray. So this is the cone, by the cone theorem. And let's contract it. So contraction CR from X to Y. And this is the contraction. Now, there are a few possibilities. So what could happen is that, so the dimension of Y, so the dimension of Y could be smaller than the dimension of X. This is like our P1 bundle case. So we have a fibration in rational curves. Well, it's a bit more subtle, but we have a fibration. So this is like the P1 bundle case. And we stop. So again, if our contraction was down, so if we were producing a fibration, then we've reached one of our target final models, and we stop. The other possibility is that CR is birational. So CR is a birational morphism. And in this case, there are two possibilities. So either CR contracts a divisor. In this case, we replace XF by Y, the push forward of F, and go to start. So maybe I should have said start. Start was here. I guess, yeah, whenever. Yeah. So CR, okay, so that's fine. The other possibility is that CR is small. So again, i.e., the exceptional locus of CR is codimension at least 2. And again, in this case, we can't just do the contraction because we break Q Cartier-ness. The canonical divisor no longer is Q Cartier. And so in this case, we replace XF by the flip, X plus F plus. So what we get is we get some sequence. So XF, X1, F1, you know, dot, 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 dot. Xn, Fn, such that each of these arrows is either a divisorial contraction, so it's contracting a divisor, a flip, or a fibration. And so this is what the minimal model program is. It's producing this possibly infinite sequence of new varieties, all linked to one another by one of these rules. Now, we can only have finitely many divisorial contractions, because every time we have a divisorial contraction, the Picard rank drops by 1. So that can only happen finitely many times. And we're assuming there's no infinite sequence of flips, so that tells us that the sequence must terminate. So termination is the statement that this algorithm terminates. Implies the algorithm terminates in a minimal model. Okay, so let me pause here before telling you. So again, as stated, this is a conjectural recipe for either making the canonical divisor of a foliation nef or realizing it as something like a P1 bundle over a lower dimensional base. So again, this is if you believe the conjectures, this is a concrete recipe for realizing the sort of stated goal of yesterday. Okay, now I guess there are a lot of moving parts to this whole story, and as written, it's not particularly concrete. But again, I want to encourage you to just hold in mind the example we first looked at the beginning of this lecture to sort of concretize what's going on here. Okay, so I'll pause here, and we'll see if there's any questions about the general workings of this beast before I tell you what is known about it. So yeah, yeah.
In the usual minimum bounded program, there's also a way of thinking about things in terms of finite generation of
Yes.
relative canonical rings. Is there something like this? Is it equivalent to that in the
Yeah. So yeah, that's a great question. Yeah. So yeah, you can think of the flip as being equivalent to saying that a certain ring is finitely generated. I didn't want to phrase it this way because finite generation is false for foliations. So yeah, maybe this is a, so for the cognoscenti, this is a good example. So here's a fact. So maybe I'll just, so there exist foliations such that KF is big in F, but the ring H, so the plural canonical ring OM-KF, this ring is not finitely generated. And this is sort of the typical case. So the reason why there is a whole finite generation perspective on these things, but the reason I didn't want to say it this way is because even if KF is big enough, finite generation fails, which is maybe like the worst possible situation. So actually this tells us that to prove any of these statements for foliations, we actually have to kind of completely invert the usual logic of the MMP. I'll try to say something about this. Well, I guess not today, but on Thursday, I suppose. But and I guess these aren't even hard examples to think of either. Actually, I mean, okay, so the easiest example is take C cross C, and then the foliation just given by projection onto C. Okay, this is a log example, but you'll believe me if I tell you you can make it not log. And then so look at K of F. So K of F is just K of C cross C over C, but look at K of F plus the diagonal. This is a big enough divisor, but it's not semi-ample. So even for, so this is not such a crazy case at all. But there are lots of examples like this. Which is pretty cool. But yeah, there are lots of other ways of thinking about the MMP. And it just turns out that this sort of perspective is the right one that works for foliations. Great. Any other questions, either about the inner workings of this machine? So yeah, like I've kind of like pulled off. I've tried to pull off the hood of the MMP for you somewhat to see how the inner workings of this thing are. And again, I want to emphasize that the MMP functions by trying to prove these 4 separate conjectures. This is the whole idea. Okay, so okay, I have 5 minutes. So let me tell you a bit about what is known, and then I'll tell you a bit more about what is known on Thursday. So I guess the first thing I should tell you about what is known, and this is a big case, is when you have the foliation with one leaf. So TF is equal to TX. So this is just the usual, I guess, the usual MMP. So in this case, KF is equal to KX. So this, I guess, is a huge program of study. This is a lot of work. Maybe, you'll forgive me if I don't write up all the names involved with it. But the punchline is that cone contraction, so yeah, one case, so cone contraction and flip theorem are all known. So we know cone contraction and flip. Termination is known in dimension 3. And that's it. There's more to be said about termination, but as stated, termination is only known in dimension 3. It's a very hard problem, it seems. Maybe. Okay, so this, and again, this is a huge amount of work. Lots of people, some people in this room, in fact, have contributed to these theorems. But this is just to say that there is one case where we do know a lot. The other case where we know something is for foliations on threefolds. So, and maybe I'll say a bit about what is known for foliations on threefolds, and then I'll end there. So now if the dimension of X is 3, and F is a foliation on X, then cone, contraction, flip, and termination are all known. So all these three things are all known, or 4 things are all known. I guess the literature is a bit scattered, so I want to try to maybe give a brief roadmap to where these things are proven in the literature. So the cone theorem in dimension F is equal to 1. This was first proven in some special cases by Bogomolov and McQuillan. And then Powell and I proved some more cases of it. The cone theorem for when the dimension of F was 2 is in my thesis. And same thing, I guess, with contraction theorem. This follows from some more work, one paper by myself and Paolo, actually, and then. So just to say that, I mean, the results are spread out across several different papers, but they're all there. So I guess I wouldn't want to write down a bunch of links to things. So you'll permit me not to be more specific. But if you're curious, please come to me and I'll talk about it some more. Okay, so I'm out of time. Thank you very much for your attention.